There are several methods of solving quadratic equations. In this video, I want to talk about three of them: factoring, quadratic formula, and the square root method. Factoring is a nice method to use in a quadratic equation that's easily factorable. The quadratic formula can be used for any quadratic equation, and the square root method is used when the equation is set up in a certain format to begin with. Let's look at an example of a quadratic equation. X squared minus 7x plus 12 can be factored into x minus 3 times x minus 4. Because we have a product that equals 0, either of these two factors could equal 0. And if I solve each of those factors, or each of those equations, I have x equals 3 or x equals 4. I can also solve this equation using the quadratic formula. The quadratic formula says that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a, in which our equation has to be set up in the format of ax squared plus bx plus c equals 0. If I solve this equation using the quadratic formula, I would have negative of b is negative 7, plus or minus the square root of negative 7 squared. Notice the parentheses reminding me that negative 7, the quantity negative 7, is being squared, minus 4 times 1 times 12 all over 2 times 1. If I simplify, I have 7 plus or minus the square root of positive 49 minus 48 all over 2, or 7 plus or minus the square root of 1 all over 2, which would simplify down to 7 plus or minus 1 all over 2. That gives me two solutions. It gives me 7 plus 1 over 2, or 7 minus 1 over 2. The first one gives me 8 over 2, which is 4, and the second gives me 6 over 2, which is 3. I have the same solutions as the other method. We can check our solutions by plugging back in the original equation to make sure that they both work in the original equation. In both methods, I said that the quadratic formula method, we have to have the equation set up in the ax squared plus bx plus c equals 0 format. The same goes for the factoring method. Let me give you a practice problem. Solve this using both methods, and then come back to the video to check your answer. This trinomial is also factorable, so I can factor into x minus 8 times x plus 4. Because I have a product that equals 0, then either factor could equal 0. And if I solve each of these equations, I have solutions of 8 or negative 4. The quadratic formula, we would have negative of negative 4, negative b, plus or minus the square root of negative 4 squared, minus 4ac all over 2a. Simplifying, I have 4 plus or minus the square root of 16 plus 128 all over 2. 4 plus or minus the square root of 144 all over 2. 4 plus or minus the square root of 144 is 12 all over 2, and I have two solutions, either 4 plus 12 over 2 is the answer, or 4 minus 12 over 2 is the solution. And if I simplify those, I have 16 over 2, which is 8, and I have negative 8 over 2, which is negative 4. So in looking at these two methods, I probably would have solved this one by factoring, just because it factored fairly easily. But we may have a problem that doesn't factor easily, or doesn't factor at all. For example, x squared plus 5x minus 8 equals 0. I can't solve this by factoring, so in this case I have to use the quadratic formula, or a method that I can use is the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Negative 5 plus or minus the square root of 25 plus 32 over 2. Negative 5 plus or minus the square root of 57 all over 2. I can't simplify square root of 57, so I'm finished. Again, this problem I could not have solved by factoring. I would have had to have used the quadratic formula. Let's look at the square root method. Here's an example. X squared equals 25. If I would take the square root of both sides of this equation, that would undo my square, giving me just x. But on the other side, I'd have the square root of 25, which is 5, but I have to include also a negative 5 in that case. So x would equal plus or minus the square root of 5. If I go back to the original problem and I plug in negative 5 and square it, I get 25. If I plug in positive 5 and square it, I get 25. So both solutions work. This problem could also be solved by factoring. If I would subtract 25 from both sides to get everything on one side, I could factor into x plus 5 times x minus 5 equals 0. So either x plus 5 equals 0 or x minus 5 equals 0, solving to give us x equals negative 5 or x equals 5. We get the same solution. And since I have it in ax squared plus bx plus c form equals 0, I could solve it by the quadratic formula. Let's look at another example. Actually, let me give this to you as a practice problem. Try to solve this one by the square root method, and then come back to the video to check your answer. In this problem, if I took the square root of both sides, because I have a quantity squared equals another value, if I take the square root of both sides, I would just have x plus 3 on the left-hand side, and on the right-hand side, plus or minus the square root of 16, which is plus or minus 4. If I subtract 3, I have negative 3 plus or minus 4, which gives me two solutions. Either I have negative 3 plus 4 or negative 3 minus 4 for solutions of 1 or negative 7. This problem could also be solved by squaring out the x squared plus 3, or the x plus 3 quantity squared, and getting all the terms on one side. If I square x plus 3, I will have x squared plus 6x plus 9 equals 16. And if I subtract 16 from both sides, I have x squared plus 6x minus 7 equals 0. This would factor into x plus 7 times x minus 1. So either x minus 7 equals 0 or x minus 1 equals 0, giving us solutions of negative 7 and 1. Also, once I get to this form, I can use quadratic formula to solve it. So you can see that we have, from just these three methods, we can solve many different problems. In fact, we can usually multiply out problems like this last problem, like our last solution method was, to either factor or use quadratic formula. Remember, quadratic formula isn't always the most efficient way of solving the problem, but it will solve all quadratic equations.